So thanks a lot to the organizers. Thanks to Ming Chuan for organizing this great event. So today I'm going to talk about asymmetric orbifolds. And I added this phrase over here, T-duality twist. This title is also the title of a paper, which is the basis of today's talk, simply because we're going to talk about closed strings of which boundary conditions are twisted by elements of the T-duality group. So I'm going to base this talk on just a couple of papers, mainly the very first one. Sorry about this. Which was released in 2015, and then one in 2014. At some recent unpublished results. I know that this has been relatively some time ago, but to conform to the theme of this conference, the geometry of string theory, so to speak, I've decided to base the talk on these two papers. But I'll mention some relations to some very recent work, such as the work by Harvey and Moore. So they wrote a paper on an uplifting discussion of T-duality or something like this. I'll say more about the relations between the results of my work and theirs and some other very recent results in the literature. So let me begin by furnishing an outline of my talk. I'll say a few words about the motivations, why asymmetric orbifolds within the context of string theory, some worldsheet aspects of asymmetric orbifolds. For most of today's talk, I'm going to focus on the worldsheet itself. And I'll introduce the notion of twist phase factors. I'll explain what are they. In the very first paper by Vafa and Samadi on asymmetric orbifolds in the early 80s, they have already mentioned the notion of this so-called twist phase factors. I'll define them more precisely later on in my slides. So this work can be considered as a more elaborate study of what they have mentioned in the paper, in the very first paper on asymmetric orbifolds. And it turns out that there is an intricate relation between these phase factors and vertex operator algebra, which I hope to also briefly discuss. The working examples of my talk will involve root lattices of Lie algebras. So I'm going to just restrict myself to the context of toroidal compactification. But presumably, these results should generalize in some suitable fashion to other string backgrounds, right, depending on what you're interested in doing. Right. There is an important relation between these phase factors, the vertex operator algebra, to the modular covariance of the orbifold theory, which is something that lies within the heart of what I'm going to discuss. And I'm going to do that at the level of one loop, string CFT. So I'm not going to talk about things like integrating over Riemann surfaces, moduli space, and all that. And then finally, I'll conclude by briefly mentioning about some implications for stringy geometry. And I saw from the schedule that there are people in the audience who work on double field theory, double formulation of sigma models and all that. And so I think to create some mutual kind of interest, hopefully this talk is interesting to them, I'll make some passing remarks on some relations on double sigma models. Okay. Right, so asymmetric orbifolds, they are orbifold backgrounds such that the orbifold twist elements act differently on the left moving and the right moving sectors of string theory. They are probably the easiest, simplest examples of non-geometric backgrounds because they don't, naively speaking, they don't emit a very obvious target space interpretation because naively you don't have such a thing called a left-moving geometry or something like this, right? So it's useful to understand how to construct such orbifold backgrounds consistently. Now, if we have a symmetry of the CFT, a natural question to ask is whether you can construct an orbifold by modeling the Hilbert space of the CFT with that symmetry. So for instance, in the case of a bosonic string, in toroidal compactification, the T-duality group is OD, DZ. If you take some generic element of OD, DZ, can you always construct an orbifold by twisting the theory with this orbifold generator. Can we always associate a fixed point with some generically asymmetric orbifold? So this was the question that was asked by Vafa and Samadhi back in the 1980s, in the very first paper on asymmetric orbifolds. And since then, there has been a very vast study of applications of asymmetric orbifolds, mainly as examples of non-geometric backgrounds. So in today's talk, I will mention something about modular covariance of one-loop string partition function at the level of the string CFT. And then I will also make some comments as to the emergence of non-commutative geometry and non-associative geometry in deep brains on asymmetric orbifold backgrounds. But I'm not going to spend a lot of time in the last point over here. There are some speculations here and there, and I just want to briefly mention some results in the literature without commenting too much because I don't understand them myself. But I think it's something that is very interesting as a future direction. So I'll make these remarks at the end of my talk. Okay. Now, let me say a few things about the phase factors. I've mentioned about these phase factors, so what are they? In this equation that you see over here, the one on the left, this refers to the one-loop partition trace, or the one-loop partition function. This G labels the insertion of an orbifold twist in the time direction. So let's take the string CFT at one loop, and let's wake rotate, and therefore the string worldsheet is Euclidean. And G refers to the insertion of the twist in a Euclidean time direction. This H over here labels the twisted sector. So you can imagine inserting a twist in the spatial direction. Right? The string worldsheet is a torus, so you have G and H. All right? Tau is the complex structure of your Euclidean string worldsheet. Okay? So let's forget about this U for the time being. All right? So these are the common variables that you encounter. Q is just e to the power of 2 pi I times tau, and L0 and L0 bar just your Virasoro generators. And then the theta L and theta R, these are twists acting independently on the right moving and left moving momenta. Okay? So of course, the orbifold twist is going to act on the oscillators as well. All right? Now, for the purpose of this talk, it turns out that they are not exactly that important. So apologies for not explaining too much about them because they're not going to affect the crucial results which I'm going to explain. Okay. So given any OD, Z group element, for instance, all right, you can read off what is theta L and theta R immediately from that matrix. All right. Of course, that assumes that you have some self-dual background, right? So let's proceed by thinking a little bit about the modular covariance of the orbifold theory. All right. So by modular covariance, this is what I meant by the theory transforming covariantly under the mapping class group. So A, B, C, D, this parameterizes your SL2, Z group element, right? So of course, on the classical geometry itself, this is of course modulo up to a negative sign. But for our purpose, it's not so important because the theories that we're going to consider, these are self-conjugate theories. Now, this relation turns out not to be obeyed by a generic asymmetric orbifold construction. In other words, if you take some generic T-duality group element and you try to construct an orbifold theory, you will not get this relation being satisfied. So a natural question to ask is then, is there something wrong with lifting the symmetry of the CFT to do an orbifold? Right? And it turns out that you can refine, in general, the T-duality group elements with some phase factors, right? Such that it becomes a necessary but not sufficient condition for the modular covariance to be satisfied. Okay. To derive this relation, you can, for instance, equate the toroidal worldsheet with this metric, sigma 1 and sigma 2 being periodic with period 1, and then you can derive this relation. Okay. Let's think about the simplest asymmetric orbifold. So let's think about just a circle compactification. but the orbifold generator being just a pure reflection on the right movers. So I'll just keep the left movers intact. Okay? So circle compactification at the self-dual radius. We know that at the self-dual point, there are enhanced symmetries and all that. What if you use this to construct an asymmetric orbifold? Can you do that? So that's a question that let's try to answer that first before talking about more general compactifications. Now on this slide, I have displayed the partition traces. This is a Z2 orbifold, so there are 4 of them. That completes your modular orbit. These partition traces, they were first presented in a paper by Simon Hellerman and Johannes Walcher quite some time ago already. Let me begin by saying a few words about the second line. So the very first one, this is just the partition function for the untwisted sector. So that's easily understood. These are your 0 modes, left and the right moving momenta. And this eta function comes from counting degrees of freedom from your oscillators. Now, what about the second line? Now, the second line, everything should make sense to string theories like, for instance, this comes from antiperiodic boundary condition because of the insertion of the twist. This counts the residual 0 modes. So if I insert the twist, we know that this T-duality group element is going to flip, exchange between the momentum and winding modes. So the ones which survive are the ones such that the winding mode is the same, the winding number is the same as your momentum number. And that explains this term over here. But what about this term, this minus 1 raised to the power of m squared? Now, it was argued that in the absence of this phase factor, so pretend that we don't think about phase factors. We just proceed usually as what we do for ordinary geometric orbifolds. All right? So you end up with the second line, but without this phase factor over here. Okay? It turns out that if you then think about this modular covariance property, this one over here, you will find that this relation is being violated. Okay? If you make an S transformation, meaning that you send tau to be minus 1 over tau, you get this partition trace. And finally, you take tau to be tau plus 1, you get the last remaining one. Now, as you can see, in the twisted sector itself, there is also a phase factor appearing. Another natural question to sort of ask is that this represents your left-moving momenta in the twisted sector. So, Simon Hellerman and Johannes Walcher wrote a paper that was titled World-Shaped Modular Folds. I think that was more than 10 years ago, trying to understand the appearance of this phase factor over here. They argued that with the inclusion of the phase factor, then this asymmetric orbifold makes sense, or at least it doesn't suffer from modular anomaly at one loop. Okay? So for a very simple class of orbifolds, once you establish the modular invariance at one loop, the higher loop will follow naturally. Right? But I guess it's natural to ask further how this generalizes to a more generic toroidal background. And where does this come from? Do you just insert them just to make sure that you have modular covariance? Is it related to something even deeper? So this cartoon over here just sketches the modular orbit that I just briefly described. Right? You begin with this insertion of the twist in the Euclidean time direction. All right? The twist phase factor will preserve the modular covariance of this theory. All right? So typically, for instance, in this case, this is just a Z2 orbifold. You don't have to check that for every single SL2, Z element, you have that relation being satisfied. You just have to check level matching condition. So the level matching condition simply means that if you begin with this partition trace, this being in the twisted sector, and you take tau to be equal to tau plus 2, then that partition trace must be equivalent to itself. Right? So this tells you how different SL2, Z elements are going to relate between the partition traces. Okay? Now, if you do not have the phase factor, then you'll find that the modular covariance relation is not being obeyed. All right, so for instance, you don't have that phase factor over here. You can always perform an S transformation to get the partition trace in the twisted sector. But level matching condition is not satisfied. Right? So for instance, if you take tau to be tau plus 1, this partition trace is not self-dual under the S transformation. Okay? So something funny happens in this particular case here. Right. Now let's think a little bit more about twist phase factors. And in our work, we showed a clear derivation of this phase factor from the viewpoint of vertex operator algebra. Right. So the way to do it is quite simple. In this particular context, this is just I'm always restricting myself to some Zn subgroup of the T-duality group. Right. Presumably, you can always generalize this to the more complicated situations. Right. V stands for your vertex operators. This G, this refers to the orbifold twist. So let's work in the diagonal basis, all right, of the twist itself. All right, so they have this eigenvalues, they are n distinct ones. And if you impose the fusion rule over here, then one can try to derive some equations which can be used to solve for these twist phase factors. Okay, so again, I must mention that this idea was first mentioned by Hellemond and Walcher some time ago, and the purpose of this work is to understand more concretely how do you actually derive a constraint equation for this phase factor in a much more general case of toroidal asymmetric orbifolds. Okay. Now let's consider the zero modes part of the vertex operators. So let's forget about the oscillators for the time being. Right? This operator over here, the alpha refers to the momentum. Right? So for instance, in the expression over here, this XR and XL, these are the so-called left and right moving parts of the center of mass coordinate of the string. Right? This alpha R and alpha L refers to the right and left moving momenta. Right? This prefactor over here is possibly operator valued. Right? If we impose the mutual locality of vertex operators, right, it turns out that you can use a relation that looks like this to preserve the mutual locality. Okay, so due to the oscillators, degrees of freedom, there's this function that goes like delta z, where delta z is the separation distance between the 2 points at which you are inserting the vertex operators, raised to the sum suitable powers of alpha r and alpha l. If you switch the position of the two vertex operators, you're going to get some extra factors, phase factors over here. So let's impose the condition that you have mutual locality, then you can derive a constraint for this epsilon, which is valued in alpha and beta. Okay? Now, if you impose the fact that the operator product expansion is associative, then you can obtain the very last condition over here. Okay. There is an interesting cohomological interpretation of these various phase factors, right? But this interpretation is not going to matter a lot in our actual computation of these phase factors. And so for this reason, I won't say much about this, but there is a way, I'll just say very briefly, for the details you can refer to the paper, that this is valued in the second cohomology of the Nanyang lattice with over U1. So this last condition over here is something like a co-boundary operator acting on this epsilon, and then you set that to be equal to 1. So epsilon is a 2 co-cycle of the second cohomology of the lattice. Okay. Right, so if you impose the fusion rule that I just mentioned, right, you diagonalize the vertex operators in the basis of your orbifold twist, impose a very simple fusion rule, then it turns out that it's not too difficult to derive some relations which will help you determine what these phase factors are, given the epsilon, right? Now, in the literature, there is, of course, a very deep and wide literature on vertex operator algebra studied by both physicists and mathematicians. This formula that I presented in our work might differ a little bit from papers written by mathematicians on vertex operator algebras, but I've also shown that it is actually equivalent by a gauge transformation. Right? So this is just a brief remark on this subtle point. So we are going to use these constraint equations, which are derived from the fusion rule that I just showed. All right? The details are a little bit complicated, so I'm not going to show like every single line of the algebra. But we're going to use these equations to try to check whether these phase factors actually make sense, in the sense that they preserve the modular covariance of the asymmetric orbifold theory. So the first thing to check is the simplest one. Does this work for the simplest asymmetric orbifold? So take a circle compactification at self-dual radius, right? We solve for this phase factor. C is some arbitrary integer, right? And this matches exactly with the phase factor which was presented in Siemens' work. Okay. So it does work for the simplest asymmetric orbifold. So the bonus is that now we get an explanation of this phase factor as being related to the mutual locality of the vertex operators, because it comes from solving equations that look like this. Okay, so N and W, these are the momentum and the winding modes. Okay. G refers to the orbifold twist. Once you know what the background is, you know what the orbifold element is, and what the toroidal lattice is, you can proceed to solve these equations. And we did that just to check for the simplest case, all right, to make sure that indeed we get the same phase factor that appears over here. Okay. Having done that, then the natural way to generalize it is to consider more general toroidal orbifolds, right? Right, so these are the usual formulas for toroidal compactification, having T-duality symmetry, this right and left moving momenta. This is your Kapmaron B field, and this is your metric. I've not displayed the dilaton because it's not exactly that important here, because we are always working with a self-dual background. The important point is that this left and right moving momenta are independently twisted by theta r and theta l. Given any generic element of OD, dz, you can read off theta r and theta l. If they are not the same, you obtain an asymmetric orbifold. The subtle point is that the orbifold theory that you obtain might suffer from a modular anomaly. Our claim is that if you refine the orbifold twist element with these phase factors related to your mutual locality condition, then it turns out that one can achieve this modular covariance relation up to some subtlety that I will mention later on. Okay. So for the working examples that we're going to deal with, I'm going to use root lattices. So these are lattices spanned by the simple roots of the algebras. All right, so for instance, over here you have A2 and G2. They are not the same, obviously, but then as root lattices, they are. Now, if we go back to this simplest asymmetric orbifold, this is a case where you only have an orbifold action on the right movers and the left movers are preserved intact. And so for most of the time, I'm going to consider just orbifolds where you only have an orbifold action, a twist, on the right movers, and then you let the left movers remain the same. Now, before doing that, let us also think a little bit about how do you obtain asymmetric orbifolds from just ordinary geometric orbifolds. If you begin with some ordinary geometric orbifold, say, let's take a T2 compactification, then you can use a study of the crystallographic symmetries to construct a wide range of geometric orbifolds at the self-dual points. If you perform T-duality along each of the direction of the target space torus, it turns out that you will immediately obtain an asymmetric orbifold. So there are some distinguished elements of the T-duality group which can achieve that. Not all elements of the T-duality group will generate an asymmetric orbifold, right? But the question of which one does is easily answered because you know how the T-duality acts on them. All right, so these are some examples of geometric orbifolds. In this case, the Kähler modulus is kept arbitrary. You don't have to constrain the B field nor the volume of the torus. and it works. You have this orbifold Z4, Z3, and Z6. There's also a Z2, all right, but that is just a direct product of your usual circle orbifold, so I did not display it over here. So if you perform a T-duality along each of the directions of your target space torus, right, you can show immediately that that exchange the complex structure and the Kähler modulus, and then the more complicated relations over here if you perform a T-duality along another direction. The asymmetric orbifolds that you obtain are characterized by the fact that this theta r is the inverse of theta L. In many papers which discusses this aspect of asymmetric orbifolds in relation to backgrounds known as T-folds and so forth, this is usually taken as the working example. You start with some geometric orbifold, you move to a T-dual frame in which the orbifold action acts differently on the left and right movers. A natural question to ask is whether there are asymmetric orbifolds in which there is no T-dual frame where you can find a geometric orbifold description. Right? So the ones that we are going to discuss very soon, you'll find that it is not possible to move to any T-dual frame such that you have a geometric orbifold description. All right, so you can do that very easily, just perform a T-duality, your background moduli remains the same, and then this lambda are just the eigenvalues of the theta r, theta L being the inverse of theta r over here. So, so apart from getting asymmetric orbifolds from geometric orbifolds by performing T-dualities right from the outset, let's take the twist to be trivial in one sector. And then just by taking a look at the OD, Z element and simplifying this matrix, all right, you can obtain a very convenient, a very simple description of the orbifold twist. So E is the sum of the metric and the Cobb-Ramon B field. But there is a constraint that all the matrix elements over here, they have to be integer valued. And therefore, it turns out that you only have a very small number of solutions to such an equation. So for instance, if you take this tau and you kind of engineer the B field such that it is equivalent to I as well, this is your Kähler modulus, then you only have these solutions being consistent asymmetric orbifold actions. So if you compare this with the slide that I've shown earlier on, you have a Z4 orbifold for tau being equal to I. That corresponds to this. The shaded area is just the fundamental domain. You can ask the question whether there is such a thing as a Z4 asymmetric orbifold along the same line. In other words, you take this to act on just the left or the right movers. And it turns out that you simply can't find a solution that has a Z4 action if you insist that the twist is trivial in one sector. Right. So this is just one example of some interesting relations which do not follow immediately from just a simple generalization. But in all the solutions that you see over here, you can always lift that solution to be that of a geometric orbifold. All right, but the converse is not true. All right, so this is what this is just a passing remark on the moduli space. So these are all Z2 elements, apart from, say, for instance, this you have a Z3 element as well. And it turns out that if you take any generic asymmetric orbifold which is consistent, they have to be expressed as product of these elements over here. Right? It turns out that they are nothing but the vowel group of A2, and then this is nothing but the vowel group of A1 cross A1. So with this observation, a natural question to ask is then whether there is a simple way to obtain the moduli space for asymmetric orbifolds in a very neat fashion. If you take the Cartan matrix of the Lie algebra up to some factor and let it be the metric itself, and if you engineer the B field in such a way that your OD, Z elements are all consistent, then you can take the vowel reflections as orbifold twists. Right. So we have checked that in all cases, indeed, you can construct consistent asymmetric orbifolds using this idea, right? So over here, I've taken the liberty to display the thinking diagrams because when we were doing this exploration, one natural question to ask is, does it always have to be a vowel reflection? And it turns out that, of course, as we know, there are also other symmetries, the outer automorphisms of the thinking diagrams, which you can possibly take as an orbifold twist element. So for instance, the Z4, a geometric orbifold that you see earlier on, it arises not from vowel reflection. Right? So all these outer automorphism groups, they are all Z2, they're all Z2 except for this D4, where the outer automorphism group is enhanced to be S3. Okay. So I've shown the simply laced one, but the non-simply laced one, it turns out that they are equivalent as root lattices to some of them over here. So for instance, G2 as a root lattice is equivalent to A2. Bn as a root lattice is equivalent to n powers of A1, and so forth. Okay. So F4 as a root lattice is equivalent to D4. Right. So based on this idea, you can also derive asymmetric orbifold backgrounds from the non-simply laced algebras, root lattices, if you wish to, depending on what you want to do. Okay. Right, so now that I've finished discussing the background moduli for this asymmetric orbifolds, sorry, there's a typo over there, let me now return to the phase factors. Because now we're going to proceed to solve for the phase factors for this asymmetric orbifolds. Okay? Now, sorry, let me get back to the previous slide first. So when we were talking about this, I mentioned the fact that we can derive these relations by imposing mutual locality of vertex operators in the untwisted sector. Right? You insert the twist in the Euclidean time direction, but you're still working in the untwisted sector. Now, the twisted sectors calculations are somewhat more subtle and more complicated. So for instance, in this case, I'm working in a twisted sector. The twisted sector is simply labeled by H. H is just some element of your orbifold group. And then K simply refers to the momenta zero modes in that twisted sector. This K tilde over here, it refers to an invariant linear combination of the untwisted momenta modes. Okay, one can show that this relation has to hold for this theory in the twisted sector to make sense. All right, so this is a sketch of this three-point function over here that relates between the vertex operators in the twisted sector and the invariant twist, the momentum that is invariant under the twist, but the momentum is valued in the untwisted sector. Right, so the OPE between the vertex operators in the twisted sector and the untwisted sector has to give a vertex operator residing in the twisted sector. As you can see, this point is rather subtle, and for this reason, it turns out to be much more difficult to derive this twist relation in the twisted sector. But once you have a theory that is modular covariant, then you simply use the modular orbit to perform a modular transformation and then rid off the phase factors in the twisted sectors. Right, so up to this point, I've talked about asymmetric orbifolds from the viewpoint of the worldsheet. Modular covariance, we talk about the twist phase factors, how they arise in principle from demanding mutual locality of the vertex operators. I've said a few words about root lattices and how you can use them to construct asymmetric orbifolds very conveniently, so you don't have to restrict to those examples which are more commonly used in the literature on non-geometric backgrounds. Right. Now, so a few more words about the modular covariance property. Right. So we have derived these phase factors with the untwisted sector as a starting point, and the phase factor that arises from the twist phase factor over here, this e to the power of 2 pi I times m times phi. This phi is some constant which we can solve by solving the equations. Right. This n equal to e times m that refers to the lattice, which is invariant under the twist, right? So if it turns out that your twist kills off all the right-moving momenta, for instance, right? Then this is the condition that you obtain. This would be the lattice, which is invariant under the twist, which will be present in this partition trace over here. And so after an S transformation, you need to do some Poisson resubmission. Then you can obtain the partition trace in the twisted sector and check whether there's level matching. Okay? So once you check that there's level matching, then depending on what your orbifold is, so for instance, if you have just a Z2 orbifold, you just have to check this being n data being equal to 2. Then you find that apart from this subtlety over here, as long as this condition is satisfied, then your orbifold theory is free from modular anomaly. Okay? But we find that even with the inclusion of these twist phase factors, there are still some constants lying around, some anomalies lying around. But the twist phase factors ensure that in all cases, you do have this relation. If you do not include twist phase factors generically, then sometimes you don't get this condition satisfied, even with this anomalous factor over here. Now, as an application to phenomenology, let's take a look at the symmetric orbifold points of Calabi-Yau compactification of the heterotic string. So now we have a T6 orbifold. So I've displayed over here some examples, right? For instance, these are nothing but just the eigenvalues of the twist, such that you have for the n equal to 1 supersymmetry. The toroidal lattice are root lattices. Okay. So a natural question to ask is this. So these geometric orbifolds are very well studied from the viewpoint of string phenomenology. Can you take that twist and let it act on just purely the right movers and or the left movers? Do you get a consistent asymmetric orbifold from this point of view? So it turns out that there are string phenomenologists who studied this problem for many years, and even last year there were a couple of very nice works which I will mention briefly at the end of the talk, which focuses on asymmetric orbifold constructions here, which potentially could be of relevance phenomenologically. So we take a look at this question here, and it turns out that we can use what we have learned so far to compute the twist phase factors for all these twists, and then to answer the question as to whether the asymmetric orbifold that you obtain as a result satisfies the modular covariance property. Of course, I'm taking a very small subgroup of the T-duality group in this case, which is O22,6, right? So it'd be very nice to generalize our results to the more general case, which have been done in a couple of papers which were released last year by a few groups. They took a look at the phase factors which were derived in this paper and started to work on these orbifold points. So we found that the case of 3 and 5, they do not admit consistent asymmetric orbifold construction. Right, so these are your non-simply laced algebra. Right, it turns out that these twist vectors over here, these are related to the outer automorphism group of your Lie algebras, Dynkin diagram. Right, so if you recall the point that I briefly mentioned when we were talking about the self-dual moduli space, we spent quite some time trying to determine whether all these Z2 elements can be used to construct asymmetric orbifolds. Because if you can use them to construct asymmetric orbifolds, you end up with a much larger class of asymmetric orbifolds. That's a simple reason. Right, it turns out that you can't. And when we try to understand the asymmetric orbifold points of these Calabi-Yau compactifications here, it turns out that they suffer from modular anomaly. So one thing that I have not talked about are your worldshed fermions. You can pretty much do a similar analysis. All right, you don't have to think about zero modes, so you just have to think about the fermionic oscillators, and there's a very natural action of the T-duality group on the fermions. So you can compute the amount of supersymmetry preserved and so forth. Okay. So some concrete examples, right? So I just want to display the phase factors here, just to kind of demonstrate that indeed you can actually obtain some explicit solutions. All right, they're not very difficult to solve, very, very simple. This E again, let me remind the audience that this is just G plus B, where B is your B field and G is your metric. So this is constructed by taking the Cartan matrix of SU4, right? And then this R1, R2, and R3, these are the Vowel reflections associated with the simple roots, right? This particular choice is simply because they generate a Z4 orbifold, all right? So there are many people studying and classifying different Vowel reflections for geometric orbifolds, potentially of a phenomenological interest. So we took some of them, and then we consider them as asymmetric orbifold backgrounds. Now you can solve the twist phase factors, and then you end up with, typically you end up with something like this, where A1, A2, A3, A4, and A5, and A6, these are arbitrary constants, right? So there are some constraint equations which you can derive easily. This big N over here, that stands for the winding and the momentum modes, winding and momentum numbers of the background. So for instance, in this case, with the insertion of the twist phase factors, with this phase factor which we solve, you can compute the residual lattice sum. Right? So this lattice sum is the one that appears in the partition function with the insertion of the trace in the Euclidean time direction. Okay. So residual simply means that you simply have those zero modes which are invariant under the twist, which will survive the insertion of the twist. All right. So it turns out that if you perform an S transformation, so you take tau to be -1 over tau, then you get the partition trace in the twisted sector. Once you have the partition trace in the twisted sector, then you can check for level matching and whether there is a modular anomaly. All right. So in this particular case, for instance, we check that indeed you have level matching condition satisfied up to some constant factor over here. So this is going to destroy your modular covariance, but typically this is not a very serious problem. Because in any realistic compactification, typically you may fiber this T6 with some other lower dimensional torus, for instance, depending on what you're doing. And then if that has a similar anomaly like this, or its inverse, then you can cancel each other such that your overall string CFT is free of modular anomalies. Okay, so this is just a point just want to mention over here. Now, we also did this calculation without inserting the twist phase factors. So just to see what happens in this case. If you don't have the twist phase factors, you can of course compute the residual lattice sum. And after performing an S transformation, doing some Poisson submission, we find that the dual lattice sum does not transform covariantly. All right, so there's no level matching condition over here. All right, so this can be interesting for people who are interested in those data functions of the root lattices. Right. In our work, we find that we have to use a result from the last notebook of Ramanujan in one of the orbifold backgrounds to try to check whether this is satisfied or not. Another concrete example, let's take the root lattice of E6. The Z3 and the Z12 orbifolds are more commonly studied from the viewpoint of string phenomenology, and all these are just your vowel reflections associated with the simple roots. This R0 being the lowest root in the extended linking diagram of E6. So corresponding to these twist elements, if you let this twist act on just purely the left or the right movers, again, the question is whether you obtain a consistent asymmetric orbifold. And we can use the equations that we developed earlier on to try to solve for the phase factors for each of these orbifolds. So this is a result of solving that equation. There are some constraints which I'm not going to kind of show because these are just the details. The crucial point is that when evaluated on the residual sublattice of E6, then the phase factor turns out to be trivial. And the dual lattice sum transforms covariantly. Right, so there is level matching. This asymmetric orbifold is consistent. Right, so this is just This is a similar story for the Z12 orbifold of E6. We also checked that there is level matching in this particular orbifold. This is somewhat more complicated, but it turns out that it can be done as well. Okay. Now, let me now move on to talk about another class of asymmetric orbifolds, which are interesting from the viewpoint of people who are interested in doing things like doubled sigma models or perhaps double field theory. And these are asymmetric shift orbifolds. So now these orbifolds are defined such that your winding and your momentum modes, right, are expressed as follows. Let me explain the various symbols that I'm using. So this delta prime and this delta prime prime over here, they refer to shifts, right, in the spatial directions. And the simplest way to view this is to think about the Euclidean worldsheet. So it has both the Euclidean time direction and the space direction. And if you shift the boundary conditions of a classical string solution by delta prime in the spatial direction and delta prime prime that is in the temporal direction, all right, for this winding modes over here, so these are like r times n, r is the radius. I'm talking about just a circle compactification here. And then this deltas with the overlined, the bar delta prime prime and the bar delta prime, they refers to shift in this winding numbers and momentum numbers. So you can construct this shift orbifolds, and these are generically Zn cross Zm orbifolds, where n and m correspond to the shifts in the winding number and the momentum number respectively. Right? So what I've shown is the zero modes contribution to the one loop partition function. You can generalize this to a general toroidal orbifold, and you can write down very similar expressions here. Okay. Right. So these phase factors that you see, all right, I've not explained very much. It turns out that you can derive them not using the very intricate machinery that we just discussed, but from very simple arguments, right? So I just mentioned this briefly due to the lack of time, right? That you also have very nice modular covariance property if you insert these phase factors over here. I've drawn this diagram because the shift orbifold is usually used as a base for a bundle structure. Right? So if you fibrate some asymmetric orbifold over a shift orbifold, and you engineer it such that these phases cancel away, then your overall asymmetric CFT can be free of modular anomalies. And that's a key point. So these shift orbifolds are rather useful. Right? They can also be used as a base for constructing T-folds. Okay, so now let me sort of just mention a few things about the doublet formulation, because I think that some of you have done very nice work on this area, so I just want to briefly mention about the relevance of this to asymmetric orbifolds. So there are various types of doublet formulation around. So one example would be the one that was formulated by Chris Howe in 2007 in this paper. And it's very nice work by Berman and Copeland in this paper where they actually try to verify some explicit claims which were discussed in Chris Howe's paper, but which was not fleshed out in detail. Right? So you begin with some double sigma model with presumably the T-dual coordinates inside your action as well. There are some extra terms, for instance, this term is that Chris Howe term as topological term and so forth. There are various types of generalizations, so I'm not going to go into that. But the key idea is that at the end of the day, one has to impose some suitable constraints to obtain the physical theory. So for instance, in this case, you obtained these constraints, and there's a proper way to do all these calculations. And so the first thing we tried was how this works for asymmetric orbifolds. It would be very nice if you can do that for asymmetric orbifolds, because these are the simplest examples of non-geometric backgrounds. Oh, okay. Okay, sorry about that. So I'll just say that after factorization, you can obtain the correct partition trace, right? Is it 1 more minute or? No, finished already. Okay. then in that case, then I'll just, yeah, no problem, it's fine. I'll just refer you to the slides if you wish to understand more.